I wanted to record this. Well, I have done very simple things. So the real stuff comes now. So I have created this for the cell, for the W. I can change this number. I have created this for the length. The resultant is W times L. So if I double click, I have W times L. And then one of the reactions, if it's symmetrical, is the resultant divided by 2. And the other reaction is the resultant divided by 2. So now I want to apply the maximum bending moment. So the maximum bending moment is W times L squared divided by 8. But I need to, in Revit, translate this to the Revit language. This is what I have to type on the formula on that field. Okay, so let's do it. So what the hell is that? No. If I select this cell, I have to type equals, parentheses. What is W? The W is this cell. It's not the number because when I change that number, I want everything to change. So that's the value. And then I type asterisks. And here I need another parenthesis. And on this parenthesis, I need to find the function of L squared. Is there a function? So here we have this fx insert function. So this is what I do. And now we need to know, again, Excel language. So what the hell is this? It's not sum, it's not average, it's not if, it's not sign. What is it? Is power. Then we go, and it's power, okay? So returns the result of a number raised to a power. Yes, so this is it. So double click on power. And what is the number? The number is the length. So I have to click on that cell. So R8 is the cell, is the length. And what is the power? It's a number. Can be to the power of 2, power of 3, power of 11. In this case, it's square, it's power 2. I click OK. Do you want to accept this correction? Yes, but we're not done yet. Okay, so here we have W times L squared. But I have to divide this by 8. Look at how many parentheses we have here. Okay, I can't zoom in because I zoom in, but only the cells. I don't zoom in here. But now I have this first parenthesis, this. So in here, I have to divide by 8. Okay, but I have to divide by 8 in the right order. So remember, we have parentheses, R6, parentheses, power, parentheses, R8, 2, close parentheses, divide 8, close parentheses. Okay, so if I have opened 3 parentheses, 1, 2, and 3, now I have to close 1, 2, and 3. And then I click OK. And there you go. 2700. I hope it's correct. Units. The units are pounds per foot. That's the units of moments. So I'm going to copy this format here. And this one, I'm going to make something even better. So those are greenish, it's fine. But this is the most important solution. So it's bright green. Okay. That's amazing because now I can change this. So it doesn't matter. Depending on your ID, you have 238 pounds per feet. Okay. And here we have 13 feet, 13.5. So everything changes accordingly. Okay. So with this, we have already calculated either this part or this part. Okay. So everything that has two unstable connections, I have calculated that bit. And I have the uniformly distributed load. Okay. If I want to make it nicer, for example, sometimes we have too many decimals. I'm going to right click here and I select format cells. And in format cells, in number, I usually want only 2 decimal places. So I do this, 2 decimal places. And then in format painter, I select 2 decimal places everywhere. But you see that I have changed the color. So I can select all these and change the color again. Well, so this, I'm highlighting this because this is the real thing that I want to copy.
I forget for the total weight, does that include the weight of the bean?
No, it doesn't. But we can include it right now. So yeah, that's a good question. But now we're going to, okay, so let's stick to this. Okay, so imagine that this is the weight of the slab plus the weight of the beam. Now we will break it down into 2 different things. But what's the goal? The goal is to select the beam. So what is the parameter that I need to select the beam? I need the section modulus. So I have to select the section modulus, S. And the section modulus is, if I remember, it's the moment, the maximum bending moment divided by the tension. I can define different things, okay? Because imagine that I can select the material. So here I have the material. I have the yield stress. Okay. So what is the material? Steel. What's the yield stress? What's the yield stress? 30. 30? 30 what? Kilopounds per inch. Inch square. Okay. So now here we have we have only this issue with the units, and we have to multiply by 12, divide by whatever. Okay. So we are going to do it once, and so once we are done with this, then we won't have this trouble anymore if we do it correctly. Okay. So that's the material steel. You can have here a different you can have different materials. You can have wood, concrete. Basically, we have steel, wood, or concrete. So you can keep adding cells, and just when we are calculating the section modulus, we have to select the right yield stress. So again, those are inputs, and we are not actually changing anything because the yield stress is it's the same. Okay, so if I'm using steel, I'm using this. So if I can do this for wood or concrete. Okay, so imagine that here I have concrete and I have wood. I will have different yield stress. I don't know because in this course we have been working with steel. But if I find out the concrete yield stress or the wood yield stress, I will write it down here, and that's it. Okay. Those units will always be kilopounds per square. Okay, so what's the section modulus? Here we have to be careful because of the units. So this is the maximum bending moment in pounds per foot, but I need this in kilopounds per inch. Okay, so if I have the maximum bending moment, but in kilopounds per inch, what do I have to do? I have to type equals. Then it's the maximum bending moment, that cell. And I have to multiply times 12 inches per foot. So times 12 inches per foot. And I have to divide by 1,000 because I have to turn pounds into kilopounds. So I do this, and this is 65. So now I use the format painter, I put it here, and we have only 2 decimal places. Okay, so this is the same value, but different units. This is kilopounds per inch. And then the section modulus is the moment, but the moment in the right units, kilopound per inch divided by kilopound divided by inch squared. And then I cancel this, yeah, it's cubic inch. So the section modulus will be equals moment divided by yield stress, and the units are inch, cubic inch. Again, I change the format of all this, and sorry? For the second modulus or for what? Is the beam and the slab. Okay, let's do it. So we're going to calculate the slab. So the slab, we have length and width. No, length, depth or thickness, and we have the weight. Okay, I'm going to put it here because the length it's in feet, the thickness it has to be foot, and the weight is pounds per cubic feet. Okay. And this is not length. I'm going to type here width. Sorry. Because the length, okay, we have a 3-dimension thing. We have the length. So I consider the length, the distance between 2 columns. The width is the dimension that we don't see. And the thickness of the slab is the thickness of the slab. Okay. So the slab is made of it's made of concrete. So what's the concrete density in pounds per cubic feet? It's 140 pounds per cubic feet or 150. Let's type 150 because it's easier to remember. Okay, so here we have 150 pounds. That's the weight, pounds per cubic feet. What's the thickness of the slab? This is what we have to calculate. If we're working with this slab, this is a metal deck. So we have the thickness of metal deck with concrete. It depends, okay? It requires 2 inches of concrete. Okay, according to this, it's 4 inches and a half. 4 inches and a half, yeah, kind of. Let's say 5 inches, but again, I can change that, okay? So let's assume that it's in foot, okay? In foot, in feet, how many feet is 5 inches? Uh, yeah, because I can put this value in inches because I have to multiply the weight is in pounds per cubic feet. Okay, so I need to turn this into, so I need like a conversion. If I have 5 inches, and again, I can, okay, so let's insert here a new cell. I can type the thickness in inches, and now I need the thickness in foot, and the conversion factor is 1 foot, 12 inches. So if I have 5 inches, that equals 5 divided by 12. 0.41 feet. If it's 6, this should be 0.5. Okay, so let's type 6 to make sure that that it works. And then the width. What's the width? I don't know. It's in this case, if I'm calculating that beam, for example, the width is the distance between half this dimension and half this dimension. So that's the width that the beam is bearing. So that depends on the project. I can say that it's 10 or 11 or whatever. Okay. So what are the inputs here? Again, I'm going to the units are not inputs, are going to be the same units. If I'm dealing with the slab, this is not the input. The width is an input. The thickness in inches is an input. This is not. So this is just a calculation, turning inches into feet. And the weight is the input because, well, we might have different kind of concretes. It can be 130, 140, 150, 135, whatever. But those are inputs. So what am I taking from here? I'm taking W. Okay. So in this W, what is it? It's the weight times, because the weight is pounds per cubic feet. So I have to multiply times the thickness times the width. So the W equals the width times the thickness in foot, not in inches. So I have to select this cell times the weight. There you go. So in this case, my W is 750 750 watts. The units are pounds per foot. Okay, so that's the weight of the slab. Now, what else? We have the beam. So what's the weight of the beam? Well, it depends. It depends. What we are doing, we are calculating the beam. So when we have the beam, we can calculate the weight. But we know that the beam weighs. So I have to make an assumption. Okay. So what is the assumption that I'm making? Imagine that I'm going to calculate this beam. This beam is quite thin. So what would be the weight of that beam? I don't know, but I do have the catalog. I can go to this catalog here. And here we have some weights, okay? So imagine that I assume that it's 50. I don't know, but let's say that the weight of the beam is 50 units, pounds per foot, okay? So the beam has a weight of 50 pounds per foot. So I select this, and all these cells, we don't need them because for the beam, I don't need the width, the thickness. The weight of the beam is always in pounds per foot. I need this for the slab because it depends on the thickness, it depends on the width, and it depends on the weight of the concrete itself. Because the units have to be pounds per foot. Okay, so this is the slab and this is the beam. And that makes 4 wrap text, no, merge and center. This is the dead load. Okay, so the dead load is made up by the weight of the slab, the weight of the beam. But we do have a live load. We do have a live load. And the live load, what is a live load in a live load in commercial buildings? Let's build here. Okay. So look at this. Here we have office buildings, classrooms. Okay, so the classroom, it's a uniformly distributed load of 3 kilonewtons per square meter. I understand perfectly what this is, but what is this number in pounds per square foot? But it's 3, we have classrooms, and this is the uniformly distributed load. This is the live load, okay? So this is people in the classroom. So it's 3 kilonewtons per square meter. 1 kilonewton is 100 kilos. I had a teacher on structures, and he told us, I am 1 kilonewton. 100 kilos, it's so, okay, that's all I needed. Okay, so every time I saw that guy, it's okay, 1 kilonewton. I'm like, this thing body, it's not even 3/4 of a kilonewton, so it's, but 1 kilonewton is something serious. But okay, so that means, look at this. 1 square meter is 1 meter. 1 meter is around 3 feet. Okay, so the live load in classrooms is 3 kilonewtons, like 4 people, like me, in 1 square meter. And 1 square meter is 3 feet. 1, 2, and 3. Okay. Do you think that it's very likely that we will have 4 people like me in 1 square meter? Likely? But it depends how many people we need for that. Yes, if it's a dance room and we are dancing very close to each other, depending on the dance, we can have this. Look at the assumptions. Okay, so we are on the safe side. We are doing this for a live load of 4 people. in a space of 3 feet by 3 feet. Yeah, on the worst case scenario, this might happen, but when can it happen? Anyway, we have to turn kilonewtons per square meter to pounds per square feet. Convert, yep. So we have 3. Convert, it's 62. Does 60 ring a bell? I think most of the exercises that we have already done, the live load is around 60. Okay, so we're not going to type 62.6563. We're going to type just 60 here. Live load, by the way, it's 60, but the units are pounds per square foot. So what do we need? We need the width, okay? So the live load in that rectangle, the rectangle is the length by the width. So in that rectangle, we have 60 pounds per square foot. So I need here the same width, 10. If I want to change only once, I can type equals and select this cell. And then I have to change only once. And for the live load, I don't change anything. But this number, because the width of the slab is the same width that I will use to calculate the live load. Okay, so what is that? That equals the width times the live load, 600. Okay, and now these are partial results. So I want to turn this into this light green. So now my W, I have to add up the dead load, the slab, the beam, the live load. So now this W is not a value that I can change. This value is equals, and I can insert this sum function, and I can drag these 3 columns or these 3 cells, and here I have the actual value. I'll do it again. Okay, so I have to add up the dead load, the live load, the dead load because of the beam, the dead load because of the slab. So I have to add everything up. And this is the cell that I have to update now. So I select that cell. It's not this, so I have to clear it. Type equals. No, not do not type equals. We can, okay, so there are different ways to do that. I can type equals, and then I can select this one plus this one plus this one. Okay, but there's a better way to do it. If you don't type equals and you just click here, the insert function, you have to insert sum. Sum is the first function that you have, the first function that you have available on Excel. So you click sum, and then you have to select all this column, all these cells, click OK, and you have 1400, the same value. If we change the width, imagine that we don't have 10 feet or between the middle of these 2 beams and the midpoint of these 2 beams. I have 12. So I change the width, 12. If I change the thickness, it's not 6, it's 4. everything changes, the section modulus F. Okay, so I don't have to do it again. So that's the beauty of working with this Excel file. Okay, so with this file, I can calculate this and this. I don't know if the load is the same and the distance is the same, the pitch will be the same. So, no problem. Yep. Oh. The sound. So we're going to calculate this case. We have L1 and L2. The materials are the same. The W can be the same, but L is going to be different. Okay. So I'm going to copy all this here. And as you can see, this is a mess, but I don't mind because this W, you see what it does? So when we copy things and paste it in a different place, what it's doing is the same thing. So this is Excel. Excel thinks that this is what we want to do. We want to copy cells and we want to keep the structure. Okay, so if we double click here, Red Excel thinks that we want to adapt these cells. So if we click here, Excel thinks that we want to adapt these cells. It's not the case. So we have to change the range of those cells. If this is some M29 to M33, we have to change. This is M3 to M7. So if I change this from M3 to M7, now we have the same, and now we do this, okay? So we click here, and we have exactly the same cells that I add up when I click here. L, it's 13.5, but now we have L1, and we're going to have L2. So let's say that this is L1. Okay, so I'm going to type here L1 just to understand what we are doing. And this is L2 because these two dimensions can be different. Okay. So L1 is this, and the L2, whatever. The units are the same. But L1 can be 10 and L2 can be 15. Okay. What about the resultant? The resultant, there will be a resultant here because now we have the uniformly distributed load, but we have two parts. So I want the resultant of L1. I don't have to do anything else because this resultant is W times L1. But the reactions are going to be different. Okay, so I'm going to delete the reaction cells because it's going to be different. But the resultant of L2, I can copy this, Control C, Control V, and it doesn't work because that resultant is, it's not this cell, it's the weight W. So I have to drag it here. Okay, so now if this L is 5 feet, this is the resultant. If this L is 20 feet, that's the resultant. And the load is always the same. The length is not. Okay, so we have L1, this distance is L1, this distance is L2. There's a resultant in the middle of L1. If of L2 here, there's another resultant in the middle of L1 there. And finally, we have this load, and this load is at this point, okay? It's the load. times this length. Okay, so those are the uniformly distributed load. And if I want to make sure that I'm doing this correctly, L1 is this one, L2 is on the right, and that load is here on the left. So I'm going to type load here. And this load is, well, it's just a value. So let's say that this is 1,000. Okay, so this value, it's something that I'm going to change because I don't know it. Okay, so it's the load is the weight of this hanger. Okay, so it's moving this down. So that's the load that we have here at the edge of this, of that overhang. And I don't know how much is it. So far I have a number and that's it. So what does it mean? Now I have to go back to the to this file. Because I'm going to explain. Let's forget about this part. Let's forget about this. We have a load here. And we have the uniformly distributed load there. Okay, so that's the problem. And I'm going to have a reaction. This is this is a reaction. Come on. And that's another reaction. Okay, so that's the problem. I have a uniformly distributed load. I have a load there at the edge of the overhang, and then I have two reactions. And now it's not symmetrical, so I have to figure out how to do it. If it's not symmetrical, I have to take moments. I have a resultant here. So this is the resultant applied in the middle of L1. And that's the resultant applied in the middle of L2. Okay, so this is L1, this is L2, and that resultant is the uniformly distributed load times, I can do this. Okay, so that's the uniformly distributed load, and I have another one here. And to make it clearer, I'm going to okay, so this is the load. Okay, so what do I want to say in this? The uniformly distributed load is the same, but the dark blue, it has a dark blue resultant, and the light blue has light blue resultant. Okay, so this one is the weight, the uniformly distributed load, W times L1, and this one is the weight times L2. To make it clearer and to understand what we are doing, I'm going to change the colors. So this resultant, it's going to be the dark blue, to dark. This one, and this is going to be the light blue. And I'm going to change this. with an updated drawing that I think it's nicer. Okay, there you go. So we have the load. I'm going to make it red. Okay, so that's the load here. Then we have the uniformly distributed load with this dark blue resultant. And that this resultant is the W times L1. And this light blue resultant is the W times L2. So what is the reactions now? Okay, so in the reaction, remember that we have to take moments about, let's say, this point. Okay. So what's the moment of this? So now I have to insert texts. So this is R1. This is R2. This is a resultant 2. That is a resultant 1. And that is the load. Okay, so we have a load, a resultant 1, resultant 2, R1 and R2. This is the same thing we have here. A resultant 1, a resultant 2, and the load. And we have R1 and R2. This is R1 and this is R2. Okay, so and now we are going to take moments here at 1. So we have the same thing, clockwise, counterclockwise. So do you agree that the load and the resultants are going to move this counterclockwise? Yes, we agree with that. And R2 are going to move it clockwise. You really mean it, or is that okay? Yeah. So thank you. So load resultant 1, resultant 2, they are moving this counterclockwise. So where is the counterclockwise thing here? Okay, so this thing counterclockwise equals the load times, and what's the distance between that load and that point? It's L1 plus L2. So that would be L1 plus L2 plus resultant 1 times, and what's the distance? It's half L1 plus L2. 0.5 L1 plus L2. So that's the distance between this resultant and this point. If this is L1, it's half the dark blue bar plus the L2. And what's left? It's resultant 2 times only half L2, 0.5 L2. Okay, so this is the counterclockwise rotation. the load, the red load, times the whole distance, L1 plus L2. Resultant one times this distance is half L1 plus L2. And resultant two is plus the times 0.5 L2. Okay, so now somehow I have to turn this into Revit language. So, oh no, let's do it first, the other one. Okay, so that's the counterclockwise, and now the clockwise is R2 times L2, and that's it. Okay, so what moves this clockwise? These force R2 times the distance L2. Okay, this is quite easy. Is it R1 or R2? Yep, you're right. It's R2. Okay, so it's R2. It's the force times the distance. Okay, so here the only unknown is R2. That's what we have to calculate. Okay, so we have to calculate R2 with this. So everything is the same. So we have the load times the distance plus, how can we do that in Revit? We can do it all at once. Or we can have something in the step that it's halfway. I'm going to do it all at once to see if you follow me. If you can follow me, I think you can. Then I will break it down, okay? But we know that R2 will be all this divided by L2, okay? So let's do that. We are in R2 equals. And now we are going to have a lot of parentheses. So we have the load times L1 plus L2. So we have the first parenthesis here. The load is this cell times, and I need another parenthesis here because it's L1, this cell, plus L2, and close parenthesis. Okay, so that's the first load times this plus this. Come on, this is the easiest part. Now it gets complicated right now. So I need another parenthesis here. So every time I add up something, I have to open another parenthesis. So plus parenthesis. What's next? It's this resultant one, times 0.5 L1 plus L2. I have to write it down because I'm going to forget it. So it's 0.5. No, it's R resultant 1 times 0.5 L1 plus L2. Okay, let's do it. So this is resultant 1. What is resultant 1? This cell here. Times parentheses. 0.5 times L1. 0.5 times L1 is this cell. close parentheses. No, do not close the parentheses yet. It's okay. I need to open another parenthesis here. Plus L2. And now I can close it. Okay, so this is what Revit does. Every time I have a function, I have to open different parentheses. What?
Yeah, you got you have two parentheses back to back.
Yep. I'm here. Oh,
So
I have to start again from scratch.
so it's load. So it's the load
It's the load
times L1
times L1
plus L2.
plus L2, but I need a parenthesis here.
Yeah, parentheses around that one too. Then you go plus parentheses 0.5.
Resultant one first. Resultant one times parentheses 0.5 times L1 and this is because it's I need to add a parenthesis here. Okay, because this 0.5 times L1, it's a parenthesis, and here resultant one times this. Okay, so I need to add another tiny parenthesis here. Now I close 0.5 times the L1, and I have to add plus L2. And now I close the parentheses. And if I click OK, it should, what?
Yes. Oh. Oh, yeah. You said your cell's not big.
Okay, the box has to be bigger. Yeah, from time to time, click OK to see if everything looks good. So far, so good. So we have already done this, okay? So we have this, load times this, plus resultant times this. And now we have this plus resultant 2 times 0.5 L2. Okay, so that's a piece of cake. That's plus parentheses resultant 2 times 0.5 times L2, this one, and close parentheses, click OK, and we have a valid number. So are we done yet? No, because now we have to divide this by what? By L2. Okay, we are calculating R2, so we have to divide all this by L2. So let's do it. But we need a parenthesis here at the beginning and another parenthesis at the end. Then I have to divide by L2. And there you go. Yeah, the problem is that we have the same boxes many times because L1 and L2 are a lot of, like, can I do in to make it this bigger? Yep, okay. So if I double click here, yeah, so that's way better. No, because everything is done clockwise. The node is counterclockwise, sorry. The resultant one is counterclockwise. The resultant is counterclockwise. This R2 is clockwise. So that's why this equals this. So that's why I have R2 and I divide all these by okay. So take some time, try to copy this. Well, this one is the load times this is L1 plus L2. Okay, that's correct. Plus this one is resultant one, this one times half L1 plus L2 plus resultant 2, this one times half L2 divided by L2. Okay, so if we look at this, it looks very easy. But, yeah. Okay. Okay. I want to calculate R1 and then on no, on Thursday. No, Thursday we have the exam, remember.
Yeah, practice.
Practice, yeah. So it's not an exam, but it's something that you have to do on your own. Okay, so I want to calculate this R1, and then we will complete the maximum bending moment. The good thing is that once we have this, we can calculate the whole structure. Then you only have to change your numbers, change the loads, the lengths, and everything will work well. So what is R1? Now this is very easy because everything that goes down equals everything that goes up. We have already calculated R2. So R2 plus R1 equals the load plus resultant 1 plus resultant 2. So R1 equals, well, let's say R1 plus R2 equals load plus resultant 1 plus resultant 2. Okay. So R1 equals all these minus R2. Okay, so that's the equation that I have to write in R1. It's quite easy. It's the load plus resultant 1 plus resultant 2 minus R2. So let's do it. R1 equals the load plus resultant 1 plus resultant 2 minus R2. And there you go. Does it make sense? I think it makes sense because R2 is significantly higher than R1. It makes sense because R2 bears more weight than R1. Okay, so that makes sense. R2 is way bigger, almost double than R1, so that makes sense. And yep, so we don't have yet the maximum moment because that will be different, but we'll figure it out. I'm going to save it. Okay, keep going. If you can do this before leaving today, it would be great. If you can't, I have recorded the video.